Hi everyone and welcome to QuantPy. We previously derived the Black Scholes formula using various alternative approaches. The formula for the price of a call option goes as follows, where D1 and D2 are given in the following formulae. Or we can rearrange the terms in the numerator to present the formulae in a more intuitive format, i.e. in terms of moneyness. We will focus on the call option as the put formula is very similar. Now, if you were asked to calculate the price of a call option, you would certainly nail it with a computer or a calculator and the normal probability tables. However, picture this. You are in the middle of a 2-hour-long meeting at the overheated offices of some hedge fund in Mayfair. Wearing that restrictive new suit which keeps bunching up your arm every time you lean over to highlight a Greek on that PowerPoint presentation. Honestly, knowing how to do a mental back-of-the-envelope approximation of the price will certainly make the difference between walking out of that plush Mayfair office with a deal you will certainly live to regret, and convincing the hedge fund that you won't be concluding the deal on the spot without running some simulations on their latest bright suggestion. So in this video, we explore and derive several approximations to the Black Scholes formula. The approximations range from the simplest that you can use to mentally calculate the price of an option, to the more sophisticated ones that you can implement in a programming language. We will arrive at some of the well-known approximation formulae. However, the approach that we intend to take in the derivation is based on pure and accessible mathematical logic, and does not necessarily follow the steps that the original developers of the formulae might have used. This is intentional. At QuantPy, we've got intuition on a pedestal, and believe that relating the steps to the mathematical logic is important, as it helps appreciate the strengths and weaknesses of the different approximations, and when to use them or not to use them. Just as a heads up, when we get to the approximations to the normal CDF, we will simply list the formulae as the underlying derivations are available in the public domain, so there isn't much value we can add there. Here is the roadmap. We will start with the simplest approximation, in which we assume the option is at the money, which will yield some neat simplifications of the D1 and D2 terms. And then we will employ Maclaurin series to approximate the normal CDF. This will give us the Brenner Subrahmanyam formula. Next, we will make the formula more accurate for none at the money options by first using Taylor series around the at the money strike. This will lead us to the Bharadia-Christofides-Salkin approximation formula, and then we will alternate between the Maclaurin series of log of S over K, which will give us the Corrado-Miller formula, and the Hallerbach formula. We will then quickly outline another variation of these approaches, which Chance came up with. It is again a Taylor series, but in strike and volatility. We will leave the details as an exercise. We will then assume that we have access to a computer, i.e. calculation of the D1 and D2 is not a problem, and focus on approximating the normal CDF. This is a well-studied problem, so we just give some well-known approximations. By the way, even if you have a software that calculates the normal CDF, it must use an approximation formula behind the scenes. So understanding the approximations is useful to appreciate the various implementations, and definitely necessary if you want to implement your own algorithm. Let's dive in. The n of D1 is essentially the normal CDF, which can be written in terms of the integral of the normal density as follows. We can split the integration interval at 0, and we know the normal probability below 0 is equal to 1/2, so we get. Now, we are in a better position because the integration limits do not have infinity. Now, we need to find a way to approximate this exponential. So naturally we recall Maclaurin series. If we retain the first two terms, this then becomes, and if u is small, then this gets close to 1. So we can substitute 1 for the exponential. Evaluating the integral, we get. Analogously, we can write n of d2 as follows. So that's the normal CDF sorted. Now we focus on simplifying the d1 and d2 terms. If we assume that the option is at the money, then the ratio inside the log function in the numerator will be equal to 1, and the log of 1 is 0. So the formula reduces to just one term. Similarly, the d2 simplifies to the same expression, but with a minus sign. So we get. Now, let's rewrite the Black Scholes formula. Substituting for the present value of the strike, we get. Factoring s out, we get. Now, substituting for n of d1 and n of d2, we get. Cancelling and combining terms, we get. And we know that 1 divided by the square root of 2 pi is equal to 0.4. And we obtain a simplified formula. And this, dear QuantPy viewers, is the well-known Brenner Subrahmanyam formula, which is a nice ace to have up one's sleeve for that mental calculation. Now, we can optimize that logic to approximate the Greeks. We know that delta is equal to n of d1, so we already had the approximation formula for the delta without even knowing it. Who said there were no free lunches in finance, eh? We factor out half and substitute 2 pi to make it easier for our mental calculation. And since there is a future use for it, let's do the same for n of d2. We know the Vega formula is as follows, where the small n represents the standard normal density, which we can expand. Now, we can substitute 1 for the exponential and simplify the numeric constants to get a simple approximate expression for the Vega. And by the way, if we substitute this Vega into the price formula, we see that the approximation to the price formula amounts to the option price being linear in Vega. So Vega times volatility is the option price. Now, if that intellectually savvy side of you had already made a note to do the same for gamma, you are definitely on the right track. Intuitively, we know when this formula won't work. The first instance where it won't work is when both the volatility and maturity are high. And this is because we approximated the exponential by 1, which is accurate only for values in the exponent close to 0. And naturally, the second instance is when the option is not at the money. This is because we assumed an at the money option in order to simplify the d1 and d2 terms, which provides a natural transition to this part, where we consider how to improve the quality of the approximations for options that are not at the money. We can adjust for this either through the Taylor series, which, as we mentioned previously, will lead us to the Bharadia-Christofides-Salkin formula, or by applying the Maclaurin series to log of s over k, which will lead us to the Corrado-Miller formula. For the first method, we will be using the Taylor series to the first order. So let's quickly recall the first derivative of the call option with respect to the strike, which is also called dual delta. So we substitute the approximation for the n of d2 to get. Now, we apply the Taylor series to the option price with a strike of k, which is not necessarily an at-the-money strike, but hopefully not too far from the at-the-money. This looks slightly complicated, but really is the Taylor series, as can be easily verified by comparing this expression to the simple Taylor series of a function of one variable. Now, we substitute the approximations for the price and the derivative. Next, we take the exponential of negative RT inside the last bracket and rearrange to get. Let's represent that present value of the strike by the letter x. With our main end goal of combining the terms containing the sigma times square root of t firmly in mind, we rearrange the terms so we get. So this is the approximation formula. We can rewrite the terms in the first bracket on the right-hand side in a more intuitive format as the average of the stock price and the strike price. So the first term is now the same formula as the Brenner Subrahmanyam, with the price of the stock replaced by the average of the stock price and the strike price. And the second term is just half of the intrinsic value. So we can see how it corrects the Brenner Subrahmanyam formula for the strike being different from the ATM strike. Classy act, isn't it? And if we substitute S0 for x, then we revert back to the Brenner Subrahmanyam formula. More frequently, this formula is used to estimate the implied volatility given the option price and other inputs. So let's isolate the sigma times square root of t on the left-hand side. And you see we get the Bharadia-Christofides-Salkin formula, which is usually written in this form, and with delta defined as follows. Square root of 2 times pi is equal to 2.5, so is 1 divided by 0.4. So the two formulae are exactly the same. And as you would have anticipated, this formula is also commonly used to approximate the initial value of implied volatility when using a numerical method to solve for the implied volatility to match the given option price. Now let's try the alternative approach. When simplifying the D1, we assumed the option is at the money. So the first term in D1 became 0. Now, to make the formula more accurate for none at the money option, we don't assume the option is at the money. Instead, we employ the Maclaurin series of log of 1 plus mu over 1 minus mu, which is as follows. We only keep the first term because we still want to simplify the formula. We first rearrange the terms inside the log to fit the Maclaurin series, which you can easily verify by simplifying the right-hand side, which implies 2s0 divided by 2x, which is the same as s0 divided by x. Now, it is in the same form as the Maclaurin series, with mu equal to s minus x divided by s plus x. Now, we can write its first order approximation easily. Substituting this into the expression for D1, we get. Now, we reproduce the approximation of n of D1, and then substitute for D1. Similarly, for the n of D2, the approximation will give. Now, we reproduce the call option formula in terms of x, which is the present value of the strike. We substitute for n of D1 and n of D2. As the terms are really parallel, we write them in terms of s minus x by multiplying each term by s minus x. Now we multiply through by sigma times square root of t to get. And we substitute y for sigma times square root of t to tidy things up a little bit. And indeed, we rearrange to combine the terms containing the various powers of y. Now we have our quadratic formula. And the coefficients of y are known constants, the solution to which we recently visited when we nailed that 750 GMAT mark, and is as follows. A note here. The usual 2a in the denominator of the last term was brought back within the square root by taking the square of 2a. Now, our expressions for a, b, and c looks slightly cluttered, but it's nothing that we can't handle. We can read b directly. 2a is just 2 times the expression for a, so the 2's cancel. And 4ac becomes easy to calculate as well. which we simplify by combining the 2's and the square roots of pi and cancelling the s plus x. Now, we need b squared minus 4ac, which again falls nicely into place when we combine the terms. And we divide it by 4a squared and obtain the full expression inside the square root. It essentially amounts to multiplying the terms by 2 pi divided by s plus x squared, which is the inverse of the square of 2a. Next, we calculate b divided by 2a, which again will soon fall nicely into place. First, we rearrange to get. Then, we rearrange the other expression as well to present it in a familiar form. And now we plug these into the quadratic root formula. We mustn't forget that y represents sigma times square root of t. The time has finally come to settle the plus minus business. If we set x equal to s0, the terms containing s0 minus x become 0, which helps simplify this further. Now, if the sign were to be minus, then this would become 0, so the solution with the minus sign is out of play. When we take the solution with the positive sign, we end up with the Brenner Subrahmanyam formula, which we can easily verify is the same formula we saw earlier. So the sign has to be positive. This is the Corrado-Miller formula. Now, the terms inside the square root can become negative, but that's not the end of the world, because we're becoming quite conversant with approximations. As a heads up, we used the first order approximation, so the approximation will not be capturing the curvature. Hence, what Corrado-Miller did was to take the 4 out and introduced a variable alpha instead, and then determined the alpha so as to obtain the right curvature. The rationale for their focus on the factor 4 becomes obvious if we use an alternative Maclaurin series for log of s over k. When we use the Maclaurin series of log of 1 plus x, we obtain the following expression in the place of alpha, which is capturing the moneyness. So we can observe how the dependence of implied volatility on moneyness can be manipulated by playing around with the alpha. The proof of the pudding is in the eating, so let's see it at play visually. Let's take a hypothetical 1-year call option on a stock, which price is 1, and which volatility is 40%. Now, we can use the Black Scholes formula to calculate the option price as a function of moneyness. Notice the strike increasing along the horizontal axis. So higher strike means lower call option price. Now, if we take the Black Scholes call option prices along the S and X and plug them into the Corrado-Miller formula, we will obtain a flat volatility curve. That's because when calculating the option prices, Black Scholes assumed constant volatility, so the approximation formula should be returning the same volatility. However, when we set alpha equal to 4, we finally obtain a curvature, because, as we recall, our approximation ignored the curvature, as our approximation was based on the first-ordered approximation. Now, hey, if we increase alpha, the curvature becomes more pronounced. On the other hand, if we decrease alpha, then the curvature reduces until we reach 1.9. The line is almost flat at around 1.9, and then it starts reversing. So the magic moment happens around 1.9. It is no surprise then that Corrado-Miller recommended a value of 2 for alpha initially. But afterwards, when another guy derived the same formula using an alternative approach, and showed that using alpha of 1.85 gives better results, they wrote another paper together saying that actually their initial analysis suggested 1.88, but they rounded it up to 2. This shows that in approximations decimals matter, as we shall see very shortly. By the way, the other guy's name is Winfried Hallerbach, and his formula is slightly different. Again, the difference is down to alpha. The x minus s is inverted, but you can rearrange the signs to get them into the same form as our formula, but the alpha indeed is different. We could extend the approximation by including another term of the Taylor series, and some people have actually done that. But as you are now fully on board with us, we are not going to pursue these approximations further. Let's turn our attention to a slightly different approach that a guy aptly named Chance came up with. That specific approach was dedicated to estimating volatility. And from the derivation steps perspective, it is more like a combination of the previous two approaches, which makes it a perfect topic to flex our burgeoning approximations muscles with. Let's quickly outline the approach so we can hurry over to the juicy bit. Chance expands the option price using second-order Taylor series in the strike and volatility, which we write in simplified order to avoid clutter. Now, we can derive the various Greeks formulae. So this is essentially a quadratic formula in terms of the change in sigma, i.e. the delta sigma in the symbols. So once we have the Greeks formulae, we can solve this expression for the delta sigma. And if we know the at-the-money volatility, then adding the delta sigma to the at-the-money vol will give us the implied volatility of the non-at-the-money option. By the way, Chance's derivation contains some typos, which have been corrected by Chambers and Nowalka in another paper. We will leave the details in case you fancy ferreting them out. By the same occasion, feel free to try an alternative approach by expanding the price formula to the second order in volatility only. Now, we take a more animation-oriented view of the approximations. So we assume that calculating D1 and D2 is not a problem, but we need to approximate the normal CDF. As we said earlier, this is unfortunately a well-studied problem, so there is a large number of approximations at our disposal. We are only going to discuss a sample, the sigmoid approximation, and the polynomial and rational approximations given in the classic handbook of mathematical functions, just to tease your taste buds. By the way, as mentioned before, even if we were using a package that has the normal CDF implemented, the algorithm would indeed be using some form of approximation, because the explicit formula for the normal CDF does not exist. The first approximation we're going to discuss is easy to relate to. We know that when we plot the normal CDF, the shape looks like a sigmoid function. So it means we can approximate the normal CDF by using some sigmoid function, where the f in the exponential means some function of x. Here is one such approximation proposed by Weisse and Rossen. If you fancy having a stab at plotting it against the normal CDF, you will see the two are visually indistinguishable. Now, we outline a polynomial and rational approximation from the handbook of mathematical functions. By the way, such approximations are commonly used for a variety of problems. First, let's represent the normal density by z. So in the first approximation, 1 transforms the x variable into a new variable, and then use the following polynomial approximation. This is valid for positive x, but given the symmetric nature of the normal CDF, knowing the values for positive x is sufficient, where the coefficients are defined as follows. And another approximation looks like this. So here we have the polynomial raised to the power of -4, And this again is defined for positive x. And coefficients are given as follows. As mentioned earlier, the normal CDF is a well-studied problem, and approximations abound. One can very easily spend many a happy moment getting acquainted with each one of them. But the trick is balancing the accuracy versus the complexity in the context of a specific problem. And that is a thrilling part. Also, people have tried applying the rational approximations to the implied volatility, but we are going to stop here. We hope you enjoyed the video and look forward to seeing you in the next.